So last week we talked about the VSEPR theory briefly. I mentioned that for VSEPR theory, the concept is that the electron pairs, no matter lone pair or bond pair, we will try to move as far away from each other as possible to minimize repulsion. That's why it will give rise to these kind of shapes. So do you go back and derive the 107.5 degree? You have learned trigonometry, right?
Yes.
So with that, you should be able to predict or calculate the bond angle, which is 107.5. So here are some examples. Alright. If let's say I have a molecule CO2, CO2 will be in a linear shape. So why is that? So that's because these two electron regions will repel each other as far away as possible to attain an angle of 180 degrees. Whereas for methane, it will be 109.5. Sorry, this one I write wrong. It should be 109.5, not 107.
Yeah.
109.5, not 107. I write wrong. And then you adopt the tetrahedral shape. Whereas for ammonia, you can see that there's a lone pair over here, and then you have 3 electron regions over here. So this repulsion would be kind of similar to this case, but not exactly the same. Alright, it is 109.5 degrees for methane, or 107 degrees for ammonia. And then for water, you can see that there are also 4 electron regions, 1, 2, 3, and 4. This angle is also somewhat similar to this, but it is at 105 degrees. Later on, we'll see why this is 107 and this is 105 degrees. So here are some steps to predict the shape of molecules. I guarantee you that if you follow all these steps, you will never get such questions wrong. Alright, never. So first step, you must be able to draw a dot and cross a Lewis structure. I already trained you on this. Next, you have to count the total number of electron regions. What do I mean by this? For example, let's say carbon dioxide. You will have 2 electron regions around the central carbon. This is 1, this is 2. Whereas for methane, it will be 1, 2, 3, and 4. Alright, and then for ammonia, it will be 1, 2, 3, and 4. Or for water, it will be 1, 2, 3, and 4. So if you know how to count these, then we can move on to the next step. We'll have to recall the basic geometry. So what's the basic geometry? If you look at this truncated table over here, if you look on the left hand side, electron region 2, 3, and 4. For those that's of 2 and of 4, you have to know. For 2, the basic shape will be linear. For 4, the basic shape will be tetrahedral. Alright, this is what I mean by basic geometry. And then next, you modify the geometry based on the number of lone pairs. So you ask yourself, how many lone pairs do I have on the central atom? For example, CO2, there's no lone pair on carbon. So therefore, it will be this one. Alright, just look at the header over here. So this means that the bond angle will be 180 degrees. And then let's say for for ammonia over here, we can see that it has 4 electron regions and 1 lone pair. So you just look for the the shape accordingly. So 4 electron region, 1 lone pair, which means you have this shape, trigonal pyramidal. And you can see that the angle will be less than 109.5. And then for water, same thing. On the central oxygen, there are 2 lone pairs. You just find this accordingly. And the bond angle will be even lesser than 109.5. And it adopts a bend shape. So that's why, based on this VSEPR theory, which is on the concept of minimizing electron repulsion, water adopts a bend shape. That's why we always draw water in this way. Alright? It will be incorrect to draw water this way. Okay? So please, if let's say the question asks you to draw the shape of water, please draw this one. Alright? If they never emphasize, they are only asking for a dot and cross, then go ahead, you can draw any shape they want. Right, depending on the emphasis of the question. So in fact, there are many other electron regions, lone pairs, etc., but you don't have to know that. You only have to know these, and these. That's all. So I already taught you how to predict the shape. Alright? So let's try practicing. Alright? So you flip to the previous part, where I ask you to draw the structure. What page is it on? Sorry, this page. Alright. Can you predict the shape of the molecules? What's the shape of Cl2? What's the shape of Cl2? What's the shape? Linear, right? And by the way, for VSEPR theory, you have to have at least 3 atoms, right? Makes sense, right? If let's say you only have 2 atoms, obviously it can only be linear. It cannot be any other thing. So the same goes for HCl, it's also linear. You know about this CH4? Tetrahedral. Alright. So if I ask for the bond angle, you will tell me it is 109.5 degrees. Although in this case I didn't draw it in a 3-dimensional way, you should know how to draw in a 3-dimensional way. Alright? Which is like that. You just have to make sure that 2 of the bonds, one of them is a hash, one of them is a wedge. Doesn't matter which one. Just select 2. You can be on the left, you can be on the right, up to you. What about CO2? Just now we learned linear. And this HCN? Linear also, right? Then OH minus will be linear also. Alright, we'll skip this because this is not your syllabus. What about H? Also linear. You can see that you only have to know those with 3 atoms, 5 atoms, but not 4 atoms. In other words, this one you don't have to know. Alright? This one adopts a trigonal planar shape, but you don't have to know. Alright? What about this PCl4 plus? Tetrahedral, right? And so on. Alright? What about this Cl2O? Take note, these kind of questions are very common. They draw in a linear way and then they ask you what shape. Obviously, the answer is not linear. Do you apply a CBR theory? The steps?
The band one.
This is band, right? It has got 4 electron regions and 2 lone pairs, similar to water. That's why it's bent. So don't be fooled by such drawings. That's why I say such drawings, right, can come in 2 forms. One is with the shape, one is without a shape. Without a shape, basically they're not emphasizing on the shape. But if they're asking for a shape, please use VSEPR theory. Alright, so enough practices for VSEPR. Alright, next, let's look at some factors affecting the bond angle. Alright, and then we'll see why the bond angles will differ. So bond angles depend on the repulsion between electron pairs about a particular central atom. The closer the electron pairs are to one another, the stronger is the repulsion and larger the bond angle. Right. Now if you compare H2O versus F2O, they have the same shape of band, correct? Based on the VSEPR theory. But in actual case, H2O's bond angle is 105 degrees, but F2O's bond angle is 103 degrees. So how do we explain this? How do we explain this? We have to make use of something that we've learned in the previous part about electronegativity. Alright? So now, if you compare F and H, which one will be more electronegative? F, right? So if F is more electronegative, this means that the shared electrons between O and F will be closer towards F, whereas this one will be closer towards O, because O is more electronegative than H. So what this means is that these 2 electron pairs, they will be closer together, right? Compared to this one, makes sense. If they are closer together, it makes sense to say that they will experience greater repulsion compared to this case. So that's why the bond angle of this is 105 degrees, this is 103 degrees. Now the reverse is also true. If let's say I were to change this to, say, oxygen and sulfur, alright? Now can you tell me which of these will have a larger bond angle? Which of these molecules will have a larger bond angle?
Sulfur.
Why sulfur?
The electronegativity is smaller than the oxygen.
And then?
So the repulsion, like the repulsion is lesser.
Yes, alright, for the same reason, if you compare F and O, F will be more electronegative. More electronegative. Right, whereas S is less electronegative. Sorry, I draw wrong. Should be further away. Alright. If you compare O and F, F is much less electronegative compared to O than S, which means that for the second case, the electrons will be closer towards F. If they are closer towards F, that means the repulsion will be weaker. Whereas for this case, the repulsion will be stronger, right? Which means this one will have a larger bond angle. So this one is probably 103 degrees. This one will be larger than 103.
So right. The repulsion of the lone pair the lone pair.
Not lone pair, the bond pair. The bond pair. The lone pair is here. The lone pair has nothing got to do with.
The repulsion of the bond pair from what?
From this bond and this bond.
Oh.
Alright? If the bond pairs are too close together, you will repel each other more, and then the bond angle will be bigger. So this.
Why do you say it's larger than 103? Then it's smaller.
Oh yeah, sorry, smaller. So probably the exact one we don't know, but maybe 100 degrees. Alright? Next part. This is the first factor that affects bond angle. The next part is the number of lone pairs present. So actually the extent of repulsion, alright, will be lone pair dash lone pair repulsion is greater than lone pair dash bond pair is greater than bond pair dash bond pair. So what do I mean by lone pair greater than lone pair bond pair greater than bond pair bond pair? This is used to explain this. Alright. So let me explain this part first. So just now we mentioned that if you compare methane, ammonia and water, all of them has got 4 electron regions, right? So based on the basic geometry, they should all be tetrahedral with a bond angle of 109.5 degrees. But how come ammonia has a bond angle of 107 degrees, whereas water has a bond angle of 105 degrees? This is mainly used to explain this phenomenon. Alright. Now if you look at methane versus ammonia, we can see that for methane, this electron pair, alright, is actually this electron pair in ammonia. So if you compare this electron pair versus this electron pair, this electron pair is actually being shared between carbon and H, right? So as long as it's shared between two atoms, these two electrons will be quite far from carbon. Compared to this case, for this case, this lone pair, is it shared with anybody? No, so it is held onto nitrogen itself. So what this means is that since electrons they repel, right, this lone pair which is closer towards nitrogen, you exert greater repulsion on these 3 bond pairs. Whereas for this case, since it's further away from this atom, you exert a weaker repulsion on these 3 bond pairs. Does that make sense? Now, if this lone pair exerts a greater repulsion, it makes sense to think that the bond angle will definitely be smaller than 109.5 degrees. So therefore, the bond angle, the actual one, is 107 degrees. So this is what I mean by lone pair bond pair is greater than bond pair bond pair. So you can see that the bond pair repulsion will be weaker than the lone pair bond pair repulsion, because lone pair is always closer to the atom. Next, what about lone pair lone pair? If you look at this case, for oxygen, same thing, it has got 4 electron regions, but then 2 of its electron pairs are lone pairs. What this means is that now instead of 1 electron pair repelling these 2 bond pairs, you have 2 of them repelling, which gives you an idea that the repulsion will be even stronger than this case, right? So that's why the bond angle they observe is 105 degrees, smaller than this and this. So we say that for this case, the lone pair repulsion is greater than lone pair bond pair repulsion is greater than bond pair repulsion. So this is what is meant by this sentence over here.
But won't like the lone pairs repel each other?
Yeah, they repel each other as well. So this repulsion on top of this repulsion will make the bond angle smaller than 109.5 and smaller than 107 degrees. Alright? So that's why lone pairs are closer to a nucleus. Alright? As is attracted by only 1 positive nuclei, so that's why it exerts a greater repulsion. Alright? So that's why the bond angle of methane, ammonia and water, they are not the same. right? So this, whatever that I've explained, is contained here. If you are still unsure, you can go back and read, or you can watch the video. Alright. So previously I mentioned factors affecting bond angle. So another factor, alright, I don't know why I put it here again, it's actually similar. For species with the same central atom, bond angles may differ depending on whether the terminal atoms are more or less electronegative than the central atoms. Right? So terminal atoms more electronegative than the central atom will draw electron density towards itself, and the bond pairs are thus further from each other and exert less repulsion, resulting in smaller bond angle. So this is exactly what I mentioned here. Right? I don't know why I put it here again. So I already mentioned this. The next factor which affects bond angle is actually the size of the terminal atoms. Now if you compare PCl3 versus Pi3, there's a missing I here, Pi3, we know that iodine is much below chlorine in the periodic table, correct? So what this means is that if you have Pi3, it's like you holding on to 3 big watermelons. The bond angle will be definitely bigger than you holding on to 3 apples, right? Correct? Just imagine. You have 3 apples, right? Each one dangling a string from the apple, from the nib of the apple. The angle between the strings will definitely be smaller compared to 3 watermelon, right? So it makes sense as well. So if let's say you change from iodine to chlorine, the bond angle will be smaller. Alright, so for this case, how do we explain it? We say that terminal atoms which are very much bigger than the central atom experiences a greater repulsion caused by the electron clouds, resulting in a larger bond angle. Alright. So this is why Pi3 will have a higher or larger bond angle than PCl3. So let's do some practices here. Right, some very simple practices. For which of the following pairs does the first species have a smaller bond angle? So what's the first step that you should do? What's the first step that you should do? You sure you're following the steps? What's the first step that I mentioned that you should do? Or the Lewis structure, right? So for this case, how we draw it? So what's the structure? You have OCl2, right? Don't pair. And SnCl2. If you compare Sn versus O, which group does Sn fall into? Sn fall into the same group, right? Sorry, Sn fall into... Sn is group number? 4, right? Basically, for SnCl2, this is what you predict, right? Correct? So which one will have a smaller bond angle? Although you have never learned this shape, but remember the concept is about minimizing repulsion, right? For O, how many electron regions does it have? 4, right? So if you compare 4 electron region versus 3 electron region, which one do you think have a smaller bond angle? 4, right? Why 4? More repulsion, right? Yes, obviously, because you have 4. So this bond angle will be definitely smaller, but you don't know what's the exact one. So for now, we'll just say that it's the same as water, which is 107 degrees. 105 degrees. Alright, this one will be larger than 105. Larger than 105. This is in fact, I think, close to 120. What about this? NF3 versus NCl3. So what's the shape of NF3? How do you draw NF3? How do you draw it? This is NF3. Remember to draw in 3D. This is NF3 just like ammonia. Alright, so please draw in 3D. And then you have NCl3.
school didn't teach us anything about 3D.
3D?
Yeah.
Then it's fine. Alright. Does your school teach?
We don't exactly have 3D, but it is somewhat like that.
Okay. Because after this part is on intermolecular forces really. Alright. So this is NF3 versus NCl3. If you compare these two, which one have a larger bond angle? Which one have a larger bond angle?
NF.
Why NF3? So for this, question is, do you use electronegativity or do you use size? If you use electronegativity, you will say that okay, fluorine is more electronegative, right? So the repulsion will be weaker compared to this. So this one will have a smaller bond angle. Right. But on the other hand, chlorine is bigger, right, than fluorine because it's below. So you can say that this bond angle is bigger. Right. Either ways, you will get the same answer. As to the first one is smaller, the second one is larger. So using either one is fine. But the general rule of thumb, this is just for information, is that for the same period, or atoms in the same period, we usually use electronegativity to explain. If let's say they are from the same group, we tend to use size to explain. What do I mean for same period? If let's say I compare fluorine and say oxygen, then I use electronegativity. But if let's say when I'm comparing fluorine and say chlorine, then I rely on size. Alright? The last one, pH3 versus NH3. So once again, you have this shape. pH3 versus NH3. So in this case, like what I mentioned just now, you should use size to explain. But for this case, does size allow you to explain? Size usually allow you to explain the terminal atom, so you still have to fall back to electronegativity. So in this case, same thing, N will be more electronegative than phosphorus because phosphorus is below nitrogen. So the lone pairs, the bond pairs will be closer towards nitrogen than for this case. It will be further away. So that's why for this case, the repulsion is greater. So this bond angle is 107 degrees, this one will be less than 107 degrees. Alright? Correct, smaller. Greater, sorry, my math cannot make it. See, now you know how long I've not used the symbol, right? Alright, so if this is confusing, then, and if let's say your school didn't emphasize this, then I guess it's okay for you not to memorize this. Alright? But if your school does, please remember how to deduce the shape as well as the bond angle. Alright? So if this is fine, we'll move on to something which is the most important in this topic, alright, on intermolecular forces. This is definitely in your syllabus and this is very, very important. Alright? So before we begin, let's try these questions. Alright, which of the following statements are true? Tick all those that applies. Spend maybe a few seconds. Within that molecule, a particular molecule. Done? Done? If you take any of these, you're wrong. Right? None of it are true.
I take the last one because I forgot if the melting point is counted as physical or chemical.
No, it's physical. Melting point, boiling point are physical.
So what's the difference between physical property and chemical property? Physical property, you can reverse it, right? For example, if you melt it, you can freeze it back. You boil it, you can condense it back. But for chemical properties, basically they are reactions and you cannot undo. For example, if you burn a fuel, you cannot unburn it to get back a fuel, right? So none of these are true. We'll go through them, alright? I mean, after I go through finish this section, you will know why they are all false. So intermolecular forces, they are forces that are responsible for interaction between simple molecules. So therefore, they are called intermolecular, right? Otherwise, it will be known as intramolecular. In other words, if you compare HCl versus HCl, the bond between H and Cl, this is known as an intramolecular force because it's within the molecule, whereas the interaction between the molecule is called inter. So the intramolecular force covalent bond is actually strong, whereas the intermolecular force is actually weak, right? It's probably at least 10 times weaker than intramolecular force. So now, unlike covalent ionic and metallic bonds, they are much weaker. Alright? If they are much weaker, it gives you an idea that if I were to supply enough energy, can I break the intramolecular force? No, right? I can only break the intermolecular force because these bonds, they are more or less, I won't say unbreakable, it's very difficult to break them. So if you supply enough energy, most probably only this interaction will be broken, whereas this interaction is still left intact. That's why when you boil water to drink, alright, you don't get hydrogen gas and oxygen gas, right? Correct. You boil water, it just become water vapor. You're actually breaking this interaction, but not the covalent bond. Otherwise, you will be drinking hydrogen and oxygen gas. So now, depending on the exact species, the types of intermolecular force as well as their strength will differ. For example, there's something called ion-dipole interaction. This is just for information. You have hydrogen bond, which is in your syllabus. You have permanent dipole. You have induced ion-induced dipole. This is for information. You have permanent dipole, induced dipole for information. And you also have induced dipole. So these two, they are collectively known as van der Waals forces. Alright? So these three you have to know. 1, 2, and 3. Yeah. Am I right that your school teaches these three?
Yeah.
Yes, right. These three know, right? I believe. So that's why I only expect these three. Alright. So next, intermolecular force is weak. Alright, I already emphasized many times compared to bonds. So during physical processes like melting, boiling, only the intermolecular force is affected, but not covalent bond. So if you compare this case versus this case, this is a solid state. Alright, this is a liquid state. If you compare solid and liquid, you can see that in the solid state there are more intermolecular force, IMF. During melting, I supply energy to break some of these IMF. The molecule itself is still intact. I'm only breaking the intermolecular force. So if there's less intermolecular force, it will become a liquid state. Now if I were to supply even more energy, I'll break even more of these IMF, and eventually I get a gaseous state. So therefore, when I boil or when I condense it, I'm only breaking or forming IMF. I'm not breaking covalent bonds. If you forget, just recall what I told you about water. When you boil water, you don't get hydrogen gas and oxygen gas. So that's why, alright, one of the options is wrong here. Alright, that's why this is wrong. Alright. So next, van der Waals forces. We'll go in depth on van der Waals forces. So far we have talked about some weak IMF. Some of these they are known as van der Waals forces. We will see how van der Waals forces, what exactly are van der Waals forces, alright, and how they form. So van der Waals forces, they are generally weak and easy to break. This gives them some interesting physical properties. Usually such molecules with weak van der Waals forces, they will have low melting and boiling points. Alright, this is because the van der Waals force between the molecules are very weak, less energy required to overcome them. That's why water, when you boil it at 100 degrees, you vaporize, right? But salt, you try boiling it at 100 degrees, doesn't vaporize. Correct? That's why we say that van der Waals force is much weaker than ionic bond. Next, it has poor electrical conductivity. Please don't try this at home. If you take very, very pure water, alright, throw in the bathtub, you see inside the bathtub, alright, and then you on the hairdryer, throw inside the bathtub. You don't try at home. Alright, disclaimer.
Why?
You die, not my problem.
Why not?
You shouldn't get.
Pure water wouldn't.
Yeah, you shouldn't get electrocuted. But please don't try this at home. I got evidence. I recorded it. You try at home, then this will be the evidence.
bathtub got impurity, even in your
Yeah,
water.
so assuming it's very clean water, your bathtub is clean.
It's impossible, no one has created ultra pure.
Yes, there is ultra pure water. You can go and search.
Huh?
There is.
If there is no ultra pure water, then
Yeah, the water is really called ultra pure water. You can go and Google it. It's called ultra pure water.
Then
Right?
you put it in some container, it doesn't
I need to
evaporate.
use ultra pure water to wash my
You know,
cells.
pure water. You know water. What is the resistance? You have learned about resistance
No.
in physics.
Learn a bit of it
Resistance.
last year.
No,
The ohm measure in ohms.
Yeah.
Yes, right. So usually your resistor is a few ohms, right? Correct. You know, pure ultra pure water. What is the resistance?
like,
It's in the range of mega ohms.
how-
Mega is 10 to the power of 6. That's how insulating pure water is. Or it doesn't conduct.
It's like,
Why doesn't it conduct? Because it doesn't contain any mobile ions or electrons, right? It's just a molecule.
the moment you're like, let's just show one minute.
Right? So simple molecules do not contain mobile electrons.
Ultra pure water for
Or some experiment. Like for example, some experiment. For example, if let's say you are measuring, you are interested to know how much ions are there in the soil, to see whether the amount of metal ions in the soil will affect plant growth. So what you do is that you can't just take the soil and dissolve it in water and then measure how much ions, right? Because there will be ions in the water as well. So you have to take ultra pure water to dissolve the soil, perform a filtration, and then analyze the filtrate. Alright.
what the heck is this?
So simple molecules do not contain mobile electrons or ions to conduct electricity. So that's why they are all poor electrical conductors. This means that carbon dioxide, ammonia, all these, they are poor conductors of electricity, right? Now, let me challenge you with this question. Alright? Listen now, the question goes like this. I have molecule A, molecule B. Molecules, not ionic, whatever. Molecule A, molecule B. When you mix them up together, it forms a solution that conducts electricity. So can you give me an example of molecule A and molecule B? These two are covalent, alright? You have in fact learned this already.
Covalent.
Molecule A, molecule B, mix them together, suddenly it conducts electricity. Molecule A by itself doesn't conduct electricity. Molecule B by itself doesn't conduct electricity. Molecule, alright?
Molecule. Graphite carbon.
You have learned it already in the last chapter.
about electron and magnetic.
Is it
Not in
magnetic?
this piece of notes.
It's inside a magnetic bonding line.
No.
I don't know, I heard that.
No, is it both bonds are covalent?
Yeah, both are covalent.
Yeah, he said both are covalent. Just now. I'm just repeating.
Don't know, right?
I'm guessing water and
Can
sodium
you-
chloride.
Okay, let me ask you another question. What's the definition of an acid?
Oh,
What's the definition of an acid?
water plus.
Are you gonna write that in your explanation question? Define acid, water plus.
No, of course
I
not.
thought it's like a
So what's
A
an acid?
substance that dissociates H
Yeah.
plus ions in water.
In water, right? So can you give me an example of an acid?
Hydrochloric acid.
HCl, right? Is HCl covalent?
Yes.
We just learned it here, right? So we have HCl, which is covalent, H2, which is covalent. Mix them up together, it conducts electricity, right? Why? Because there is H plus and Cl minus. Am I right? Am I right?
I feel so dumb.
I'm learning already. Why are you think so hard? Why are you think so hard?
forgot about acid. Oh my
So
god.
that is me at chem papers, like having done all the content. Then I learned the questions, wait.
Looks familiar, right?
How have I been learning the whole year?
Okay, next, let's talk about factors affecting the strength of van der Waals forces. Alright? So the first factor which affects van der Waals forces, alright, is the number of electrons. So it goes that the greater the number of electrons, the stronger the van der Waals forces. So if you compare the noble gas, helium, neon, argon, krypton, these are the AR, atomic number, sorry, atomic mass. And you can see that the boiling point basically increases. Alright? So what actually causes van der Waals forces? Just for information, I think you might not learn this. Have you ever wondered, how come molecules, these are molecules, for example neon, these molecules, right, they are electron rich. In other words, they have a lot of electrons in the electron cloud. These one also have a lot of electrons in the electron cloud, right? What makes you think that they will attract each other by a force?
The positive.
Have you ever wondered such a question?
No.
I have atom A, atom B. Both have a lot of electrons. Why would they attract each other?
Because they like each other.
Actually makes sense sometimes.
So why? That's because although you have electrons, the distribution might not be even. You cannot say that, I evenly distribute this number of electrons within that spherical shape. No. So what actually happens is that most of the time, one part of the molecule or one part of the atom will get slightly more electrons than the other part. So this is still neon. Let's imagine that there are more electrons on the right hand side, alright? More electrons. And there are less electrons on the left hand side. Correct? So if there are more electrons on the right hand side, we can say that this part will be slightly more negative, right, than the left hand side. So on the contrary, on the left hand side you have a delta plus, because whenever I have a delta minus, I must have a delta plus to balance the charge. So what can happen is that this part of neon, which has more electrons, you tend to repel another part with more electrons, right? So what happens is that if let's say I have a neighboring neon, I won't draw here, just copy paste. Alright. If let's say I have a neighboring neon,
Copy paste indeed.
oops,
Whoa.
become a fat neon. Alright. If let's say I have another neon beside it, this part will repel the electron from this part towards this side, right? Because there's more electron. So now this part I also have a delta plus. Can you still recall that previously I mentioned that if you have a delta plus and delta minus, there will be some form of attraction? Yes, right. So actually this gives rise to your van der Waals forces.
So basically the delta minus side creates the delta plus side on the other end.
Yes. So that's why this is actually known as instantaneous dipole-induced dipole interaction.
Creating your own partner.
Yes, correct. But have you learned this? No, right? So that's why I don't teach you this. Previously I have all this in my notes, and then I realized a lot of students, they just get stuck.
Technically you just taught us that.
Alright.
Technically you just taught us that, but okay.
So this time around I just cut away all those parts. So now you only have to know that the greater the number of electrons, the stronger. So pictorially, why when there are more electrons, the van der Waals will be stronger? Just imagine if let's say you have 2 electrons. Alright, 2 electrons. It's very likely that one on each side, correct? It's very difficult to unevenly distribute them. But if let's say you have more electrons, there's a greater chance that on the left hand side you have more electrons, or on the right hand side there's more electrons, correct? So that's why there's a greater chance for the van der Waals forces to act upon. So hence, yeah, stronger attraction. Alright? So you can say that if let's say I have 2 electrons, at most I have both electrons on one side, no electrons on the other side. But if let's say I have 100 electrons, it's possible that I have much more electrons on one side than electrons on the other side. So the attraction is actually much stronger. So that's why the electron cloud, or rather number of electrons, affects the strength of van der Waals forces. The next factor which affects the strength of van der Waals is actually surface area. So now for molecules with the same number, this is used when let's say this doesn't help you to determine which one has a stronger van der Waals. For example, these 2 molecules over here. If you look at these 2 molecules over here, what can you tell me? They have the same number of electrons. You can go and count. They have the same number of carbon, same number of hydrogen. Which means you cannot judge which one have a higher melting point, boiling point using the first factor. So what you do is that you use the second factor known as surface area. Now if you compare these 2 molecules, the molecule on the left hand side is like a cylindrical shape, right? Like this case. Whereas for the second case, it is more like a spherical shape. If you compare the cylindrical shape versus the spherical shape, what do you realize? You realize that there's greater surface area for van der Waals to act upon, right? For the first molecule, then for the second molecule. Correct? So therefore, the greater the surface area for van der Waals to act upon, the stronger the van der Waals force. Alright? So therefore, we say that for molecules with the same number of electrons, branching introduces smaller surface area. Alright? So for this compound is known as a branched compound. Quite obvious why it is called branch, right?
Because it looks like a
Looks like branch. Because for this case, it's called a linear compound.
It looks like a chicken foot.
Linear because you can draw in one line. Branch because you cannot connect all the atoms in one line, right? Without bypassing the atom that you have already drawn. Alright? So that's why this
second one looks like a chicken.
one is this one, this one is this one. Alright? So that's why for branch one, his van der Waals force is weaker than unbranched one. but I believe for the number of electrons you should cover. Right? Also don't.
They don't go into factors.
See whether you want to buy insurance. So I already mentioned just now, alright, there are actually two types of van der Waals forces. This one is just for information to have to know. The first type is known as instantaneous dipole, induced dipole. The second case is known as permanent dipole, permanent dipole. Alright, this is just for information. If you are interested, you can ask me. Alright. So the next kind is known as hydrogen bonding. All of you learn hydrogen bonding?
I hate
Yes, right?
hydrogen bonding.
This is the one thing I actually remember.
So hydrogen bonding,
This was me becoming well not sure.
So how does hydrogen bonding arise?
When there's hydrogen.
Alright. So the NH, OH and FH bonds, they are very polar. Can you still remember what's the meaning of polar? The electronegativity difference will be very great, right?
Then, but it's less than 1.
Why very big? Because of the highly electronegative F, O, and N. In fact, F, O, and N, they are the three most electronegative atoms.
Yeah.
So what this means is that, if let's say I have fluorine, alright, bonded to hydrogen, the electron pair will be very close to fluorine. So fluorine have a delta minus, hydrogen have a delta plus. Alright? And then what happens is that if let's say I have this scenario, alright, is it very cold?
For me,
You can
Most
increase
surprising
the,
today I'm not
you can increase the temperature, if not it's gonna freeze.
Surprising today is not me there.
Alright?
because I'm wearing a DNT.
So why are you using that? It doesn't have any color.
Wait, what's that actually?
It's an ionizer.
Makes you cooler, you're already very cool.
It
It's an-
literally blows in your face.
It's an ionizer.
So what does ionizer do?
It just basically removes the bad stuff in the air. As my mom claims.
Oh,
Like so-called air purifier.
Yes.
But does it purify your brain?
No.
It works.
It works.
It works at least. It works at least.
It works in purifying the air, not the brain.
Okay, let's look at this. If let's say we have HF, alright, we can see that on H there's a delta plus. So what it can do is that it can attract another lone pair from a neighboring species. For example, especially oxygen, nitrogen, and fluorine. Alright, so hydrogen bond is defined as this bond. The interaction between H on FON and a lone pair on FON. Layman's term. Let me write it here. H on F, O, or N interact with lone pair on F, O, or N. In layman's term, this is the definition of hydrogen bond. So for this side, same thing. You can see that you have H on O, right? And then this H is interacting with the lone pair on F. So it can be this or this.
So your mom decided that thing was enough to purify the haze volume.
Not enough. So once again, take note that hydrogen bonds, they are usually the strongest type of intermolecular force. Alright. In other words, this is stronger than van der Waals forces.
It's the strongest among the weak forces.
Yes. Usually,
Quite a bit.
take note, I'm very careful with my words. Usually. Doesn't mean all the time. That's why water, it boils at 100 degrees. Like carbon dioxide, it boils at probably negative something. Why? Because there's no hydrogen bonding in carbon dioxide, but there's hydrogen bonding in water.
You wondering why I stopped saying what the bonding.
So generally speaking, the hydrogen bond strength follows the order of electronegativity. What this means is that the hydrogen, fluorine, hydrogen bond is stronger than hydrogen. I forgot to draw a lone pair.
The electronegativity is F greater than O than N.
Yes, correct. So it follows the same trend. So hydrogen bond strength also follows the same trend. In other words, HF hydrogen bond is stronger than HO hydrogen bond is stronger than HN hydrogen bond. Why is that so? Pretty much obvious, right? I mentioned that F being the most electronegative is delta minus delta plus will be the greatest. Whereas O is less electronegative and N is the least electronegative amongst the three. So it makes sense to think that the interaction will be stronger for HF, weaker for this, and weaker for this. Alright? So with this in mind, let's try this question. Alright? Which of following molecules cannot form hydrogen bond with water? Right, cannot. Take note that these structures might not be correct. First of all, because it's kind of common that the teachers purposely leave out lone pairs because they assume they should know where the lone pairs are. So you have to fill in the lone pairs. Alright. I'm also kind of cold.
Isn't it just the one molecule?
So which of these cannot form hydrogen bond in water?
Everything except this one
For the first one, alright.
I say cannot.
For the first one, how does it form hydrogen bond in water? Can you please draw it out?
I don't think can.
Can this form hydrogen bond in water?
No.
What's the definition of hydrogen bond? Layman's term.
Yes.
Let's say we draw the water here.
FON that has bond with hydrogen.
So the definition is H on FON, right? Interact with lone pair on F or N. So you have a lone pair on F or N, right? You have a H on N, right? So why can't it form?
No.
Or lone pair. There's a lone pair oxygen, right? Which of these cannot form hydrogen bond with water?
With water.
Water has a lone pair, right? So now you satisfy this criteria, right?
I see.
You satisfy this criteria, right? Do you have H on F or N? Yes, right? You have H on N. So why can't it form? Can, right? That's why I write that layman's term there. Because a lot of students think that this cannot form because there's no lone pair on N. Doesn't matter what. I'm not asking for lone pair on N. I'm only asking for a H on F or N. So basically this can form hydrogen bond with water because water has a lone pair.
I like how water was a question that I forgot water existed.
Alright.
I like the fact that
And when you are drawing hydrogen bond, take note, all these you must include. Alright, you must have a delta minus, you must have a delta plus, and then you must label that this is hydrogen bond. And you have to draw the dotted the interaction. Alright, as well as the lone pair. You miss out any of these 0 marks. So now let me change the question. Can this molecule form hydrogen bond with another of its molecules?
Why is that delta plus and why is that delta minus?
This delta minus is because O is electronegative, right? Compared to H. So you have a delta minus. This H is electropositive compared to this N, so you have a delta plus.
I don't think it can form a hydrogen bond.
Can this molecule, alright, form hydrogen bond with itself? No, right? There's no lone pair. Although there's H connected to N, but there's no lone pair anyway. So if let's say have another of these molecules, it cannot interact with itself via hydrogen bonding.
Isn't one of it additive bond?
So
Wait, I don't get it. Why can it like form with water but not form with...
because water has a lone pair, right? If you draw another molecule of itself, does it have lone pair? On F or N? Doesn't, right?
Ah, wait, lone pair not.
Because
correct.
for the structure of these, alright, for ammonium, ammonium, 3 of the electrons, alright, they are shared 1 electron each, and then for the last one, both electrons shared come from nitrogen. So it doesn't have any extra lone pair to interact. What about this molecule over here?
Like non and all.
Does it have any lone pair or any atom? Yes, right? Although I didn't explicitly draw it.
Yeah.
There's a lone pair on this nitrogen.
No, not connected to H.
You have H, O, H. So am I violating any principle? You have a lone pair on N, right?
Yeah.
So we satisfy the second criteria. Lone pair on F or N. What about the first one? Do I have a H on F or N? Yes, right? I have a H on O. Correct? So in fact, these two can interact this way, right? Why not?
Okay, never mind.
This is confused.
This is delta plus, delta minus, delta minus.
You feel cheated.
Am I breaking any rule? No, right? I'm just merely following the instruction. I thought Singaporeans are very good at following instructions.
I'm not even Singaporean.
If you don't understand, you should know how to follow. Because I can feel.
What about this case?
For Malaysia.
Adrian is like always reminding us.
What's this case?
Yes.
How about this case?
Which case?
There's a lone pair on F on O, right?
Can,
so you can interact with water, right? Once again. Now, can this molecule interact with itself via hydrogen bonds?
No.
There are so many hydrogens here, can
Yeah.
read the definition again. H on what?
H on F or yeah, cannot.
Are these F, O, and No, right?
No, it's not. It's on C.
It's basically really following the instructions. The manual says this, then it does apply this. The manual doesn't say it, then it doesn't work. You have to trust my wise words, alright? I already summarized them.
Why is there 2 delta minus and 1 delta?
Okay, this one?
Yeah.
Actually, this is delta minus, this is delta plus. Just that we are more or less interested only in the hydrogen bond part, this part. Alright? So that's why if let's say you have questions asking you to draw the hydrogen bond interaction between 2HF, alright, the best answer would be to draw all the delta plus, all the delta minus, the lone pairs, draw everything, interact, label this as hydrogen bond. Alright, you'll get the mark. If you miss out anything, you wouldn't get a mark. These questions here is just to show you the possibilities of hydrogen bonds, right? Which a lot of students think that they cannot form, but in fact they can. Now, what this means is that these molecules will tend to be soluble in water because they interact with water. Alright. Now, what about this case? Can you form hydrogen bond with water? Can, right? You have this oxygen which can interact with hydrogen or water. And you have this hydrogen which can interact with the oxygen or water, both of which satisfy the criteria of hydrogen bond, right?
Yes.
So then I ask you, can this molecule hydrogen bond with itself? With another molecule?
Yeah.
Can, right? Because you have O, you have H. It satisfies the criteria. Basically, you can have another molecule, the O interact with the H, or that this H interact with that O. The last one, SF4. Can this interact with water?
Yeah.
Yes, right. You have lone pair on fluorine. Lone pair on fluorine. And you can basically have HOH interacting. Delta minus, delta plus, delta minus, right? No big deal.
Alamak. What's for? The PSI in this region is
Yeah. So now we have finished our intermolecular force part. Let's compare the van der Waals and hydrogen bonds. Alright, with the table. So van der Waals forces occurs between what kind of molecules? For hydrogen bond already listed, it can only occur between molecules with OH, HO, HN, HF, and the lone pair on O and F. Then you can have hydrogen bond. Then what molecules will have van der Waals? This is to allow you to compare the correct intermolecular force. Alright. Basically for van der Waals, it occurs between all molecules. Alright. Take note, why you have to make sure that your answers for your test or whatsoever goes with the logic. Say for example, if I ask you to compare the boiling point of water versus carbon dioxide, do you use van der Waals to explain?
Yeah.
Are you going to say that water whose mass is 18, alright, whereas CO2 whose mass is 44,
Use the bond.
and then you'll say that CO2 has a bigger electron cloud size, therefore stronger van der Waals. So carbon dioxide has a stronger van der Waals force and hence a higher melting point or boiling point. Are you going to say that? No, right? You're stepping yourself in the feet. Both of them has van der Waals forces, but only water has got hydrogen bond. Previously, I already mentioned that hydrogen bond is usually very strong. So therefore, for this case, we only talk about hydrogen bond. We say that for water, hydrogen bond exists between water molecules, which is strong, very hard to break. Whereas for van der Waals, whereas for carbon dioxide, only van der Waals exists between the molecules, which is weak. So therefore, less energy is required to be broken. Alright? We will look at some examples later, so no worries. So, but now you have to appreciate that for van der Waals exists between all, hydrogen bond is only between F1N and a hydrogen on F1N.
Appreciate.
So, van der Waals is due to what? This part I already mentioned, you don't have to know. Yeah, sure. So for van der Waals is due to this part, you don't have to know, so I wouldn't fill in this blank. It's basically the one that I've drawn, the neon, that one. Right, but you don't have to know why it's caused by. What about hydrogen bonding?
The one that created the partner.
Hydrogen bonding is due to?
Hydrogen.
Is due to what?
Electronegativity.
Sorry? How do I phrase into words now?
You wrote
Yeah, this one, alright. How it's formed. So I will not copy paste. Right. Most likely you won't be, I will say that you will not be asked on the definition of hydrogen bond. It is no point asking you what is a hydrogen bond. You will most likely come in forms like this to see whether you really understand hydrogen bond or know how to apply. Alright? Trust me, there won't be a question asked you to explain how hydrogen bond is formed.
Majority of the time when I see hydrogen bonds, I just see got N, got F.
So what about strength wise? Strength already said that van der Waals force is generally weak. Generally. Whereas hydrogen bond is generally strong. This means that there are exceptions whenever I use the word generally.
What's the example?
For example, we have learned about, for example, iodine, alright? I2. Is there hydrogen bond in iodine?
No.
Right? Definitely no. But iodine, we know that it exists as a solid at room temperature, right?
Yeah.
It's a purple solid, or dark, almost dark black solid. But why is iodine a solid but water a liquid? This means that iodine must have higher boiling point, right?
Yes.
Than water. So this also means that the intermolecular force in iodine is stronger than that of water. Right? But we know that iodine is van der Waals force, but water is hydrogen bonding. So in this case, we can say that the van der Waals force is stronger than the hydrogen bonding. Alright, when the size overwhelms the hydrogen bonding. So that's why you have to be flexible in your answer. Don't always think that hydrogen bond is the strongest. No. Right? There are a lot of circumstances whereby it's not the strongest of the two. So some examples of van der Waals force, very simple, just now I already gave you. I2, H2O, HCl, neon, CO2, CH4, etc. What about van der Waals force? What about hydrogen bonding? H2O, we have learned about HF, we have learned about ammonia, these three. Of course, it's not limited to these three only. So you can see that there are some overlaps, right? We have H2O on the left and H2O on the right. But majority comes from hydrogen bonding because hydrogen bonding is generally stronger than van der Waals. Alright? So what is the factor that affects van der Waals strength? Just now we have seen. The first is number of electrons.
Surface
Or basically the molar mass. Alright? This is a good estimate of the number of electrons. Second one is surface area. Bigger the surface area for van der Waals to act upon, the stronger the van der Waals. Whereas for hydrogen bond, it's affected by, basically H cannot change. It's basically affected by F or O or N. I already gave you the trend over here.
You know, we are doing this chemistry paper and then I'm just terribly weak at chemical calculations. So how do you do this question? This is the second question. Conduct chemical.
Oh yeah. Deduce the types of intermolecular force for all the molecules in the previous concept application. So if you look at these questions, these molecules, can you deduce for me what is the predominant type of intermolecular force present? Yes, the predominant one. So for chlorine, Van der Waals, right? Cannot form hydrogen bond definitely. How about HCl?
Van der Waals.
Can it form hydrogen bond?
Yes.
No.
Between like H and another chlorine? Cannot. Cannot, right?
No.
It must be between H and F, O or N. This CH4?
Van der Waals.
Van der Waals, right?
Van der Waals.
Then CO2? Van der Waals, once again.
Our form teacher look at our published schedule and they should like, no, you guys have too much work lessons. You guys should get some rest. And we're like, okay.
So if you compare these two,
What's rest?
so if you compare these two, which one will have a higher boiling point?
CH4.
C4.
Because
No, wait, no. Size?
If based only on size, then CL should have the higher one. Confusing you.
which one will have a higher boiling point?
CH4 because CL is bigger than CH, and then CH4 has more electrons being on the bigger number.
Count the number of electrons.
2, 4, 8.
You sure you only count those that's in the bond?
Oh yeah. Right. That's that. Actually, him answer the question.
So which one have a higher boiling point?
Probably.
Make use of what I told you just now, right? What are the factors affecting the strength of Van der Waals? Electrons and surface area, right? For this case, does number of electrons allow you to determine?
No.
Why not? How many electrons does chlorine 2 contain? Do you just count these electrons?
No.
If you only count these electrons, then you are telling me that for iodine, you have the same number of electrons of chlorine, is it?
14 electrons.
How many electrons are there around chlorine? Do I say that neon contains 2 electrons? Sorry, the noble gas all contains 8 electrons each. Do I say that? What did I mention? Look at here. I already gave you the concept, right? Do I say that neon, oh it has about 8 valence electrons, so its electron is 8. Krypton, valence electron 8, so therefore it has 8 electrons.
Oh, yeah.
How many electrons does chlorine Cl2 contain? Why you all never look at the periodic table? Isn't it a very simple question? How many electrons does chlorine contain?
Chlorine contains.
Chlorine has 38.
No.
No.
Chlorine has 70.
Nobody take periodic table, surprisingly.
Chlorine has 70.
It's an easy question. You should
Chlorine
know
has
from
higher.
lower sec. How many electrons does this have? 34, right?
34.
Think about CH4. How many electrons does it have?
20.
10.
Hmm?
10. 10.
You say 20, then you say 10. So it's what?
I start.
How many electrons does it have? 10, right? So, which one have a stronger Van der Waals?
Yeah.
Chlorine, right? Because yes, more electrons. That's all right. Why is it so difficult?
Because there's a devil right next to him.
Why if you compare these two? CO2 versus chlorine, which one will have a higher boiling point?
CO2. I guess. Oh. Never mind. Chlorine still has a higher one.
Chlorine got how many electrons?
34.
34, right? CO2?
CO2 has 24.
24?
Yeah.
24? How do you get 24?
Electrons what? Wait. Alamak.
Hey, if you all don't know how to do this, you can go back to lower sec.
Alamak, sorry. Sorry.
Huh? 22, right? You sure 22? Electrons?
Yeah.
How many electrons does carbon have?
I want to cover it.
What about oxygen? 8, right? 8 plus 6 give you 14. 14 plus 8 give you 22, right? Isn't it just like that? Why are you taking so long to...
8 plus 8 plus 14. What?
Isn't it just like that? So therefore, I just taught you how to determine which one has a higher boiling point based on the number of electrons. You just have to count the number of electrons. Alright? We'll look at more of such questions later. So let's look at the effects of hydrogen bonding on physical properties. Alright? Or why hydrogen bonding is important. So since hydrogen bonds are generally a strong type of intermolecular force, the presence of hydrogen bond can give rise to some interesting properties. So the first interesting property that we observe is actually the trend in the boiling point of hydrides. Hydrides are those basically containing hydrogen. Now if you look at the black line, you can see that for the last 3 atoms, as for the last 3 molecules, it is an increasing trend, right? You would expect H2O to be somewhere here, right? Probably. But how come H2O's boiling point is so much higher than even the heaviest H2 hydrogen bond, right? Same thing for H2O, hydrogen bond. What about these 3? Can they undergo hydrogen bond? No, right? All of them are van der Waals. Just now we already mentioned hydrogen bond is stronger than van der Waals. Correct, huh? Now, what about these 3? How come these 3 they get higher and higher? How come this one is higher than this one is higher than this one?
Going down.
More electrons, right? So we already learned this as well. Next, for the dotted line in the middle, you can see that ammonia, same thing, is higher than this, higher than this and this, right? So why do you think the trend is like that, increasing for these 3? For the same reason, right? As these 3. Right? So why does ammonia has a higher boiling point than these 3? Than these 2 at least, hydrogen bond once again. Alright? Now if you look at the last one more or less follows the trend of increasing. So why does CH4 not exist somewhere up there? It's because there's no hydrogen bond, right? So all of these are van der Waals. So this explains the trend. Now the question that I'm going to ask you is that why does this have a higher boiling point than this and then this?
Because the total number of electrons is...
You sure? You want to go and calculate?
I'm going to check the
Surface
periodic.
area.
No, because
It's increasing groups, so there is a more electrons.
More electrons, right?
Yeah.
Basically, if you look at your electrons, you can see that there's more electrons. Alright, although slightly. Alright. So therefore, you should be able to do all these questions already. Explain why boiling points of group 14 hydrides increases from CH4 to SNH4. In other words, the bottommost line. Alright, why does it increase? That's because of the greater number of electrons, right?
yeah.
So you have to know how to explain. So the main type of intermolecular force between group 14 hydrides is van der Waals forces. Alright? So the increase in boiling point is due to increase group 14. 1-4. Take note, for periodic table, if you have learned the periodic table, that chapter, you should know that the periodic table can either be arranged in the Roman numerals or these Arabic numerals. So this group 14 is equivalent to group 4. Alright, in the Roman
I learned
numerals.
that topic already, but my school didn't cover one.
I'll send it our clarification. You know in the center you saw the periodic table, it's group 1, group 2, and then the 3, group 4. Screw that. Now it's all the way through.
Because the problem with Roman numerals is that you cannot assign the middle section. You realize all the transition elements. So therefore, they use this 1, 2, 3 because if you use 1, 2, 3, you can cover the transition elements as well.
No, for us we have to use Roman.
So the increase in boiling point is due to the increase in van der Waals forces. Alright. Since the number of electrons from CH4 to SNH4 increases. So next one, why does boiling point decrease in the order H2O, NH3 and CH4? So first you have to say that CH4, van der Waals, these two hydrogen bond, and then you have to compare these two. Alright. Why this one has a stronger hydrogen bond than this one? Just now already mentioned, right? Because O is more electronegative based on the trend, which I already taught you as well. So first we settle this versus this. Right? H2O and NH3 have, alright, see my English not very powerful. Higher boiling point due to hydrogen bonding present between the molecules. Hydrogen bonds are stronger than the van der Waals forces present between CH4 molecules. Alright. Hence H2O and ammonia have higher boiling points. And then next we compare H2O and ammonia. Alright. So we say that H2O forms stronger hydrogen bond than ammonia, as oxygen is more electronegative than nitrogen. So yeah. You can go ahead and say that, alright, or you can say that the OH bond is more polar, alright, then NH bond, thus hydrogen bond formed is stronger. Alright.
Yeah, I also have that.
So this is the first interesting phenomena. Next one, we can actually use hydrogen bond to explain, why ice floats on water. Have you wondered?
No.
Both ice and water, they are H2O, but how come ice is less dense than water?
Cause contraction.
You know how ice, when you freeze water, the ice always comes for the
Finish reading? Alright, let's talk about the open structure of ice. So now, most liquids, they are less dense than when they are in the solid state. This is because regularly arranged solids, alright, occupy less space. Alright, but water occupies more space when it's frozen. That's why when you freeze water into ice cubes in the fridge, you start with a relatively flat surface on your ice tray, but after you freeze it, it's like bulging out a bit. It's due to the expansion when it freezes. That's why you shouldn't freeze things inside a glass container. Otherwise the glass might crack or shatter. Especially in winter countries.
I saw how to freeze like ice until then.
Oh, in winter country that time in Korea, right? Then after that when we place the bottles of water in the car, then the next morning when we come back to the, not the car, the bus, next morning when we come back into the excursion bus, it's like bottles of ice. Literally like it's like still a bit of water on the outside, but the ice inside is like the bottle shape. Then with a bit of water.
I saw
Then we are okay, there goes our mineral water.
Yeah, so actually due to hydrogen bonding, ice adopts an open structure. So usually we think that in the liquid state, all the molecules are arranged randomly, right? And then when it freezes, probably there's some regularity. So for water, when you freeze it from the irregular arrangement in the liquid state, it actually forms this very regular arrangement. So each of these is actually a water molecule. And you can see that these dotted lines they are actually hydrogen bonds. So you have a hydrogen bond between the oxygen and a hydrogen on another one, etc. to form this kind of extended hexagonal network. So it's actually a lot of hexagons separating them. So each central oxygen atom in H2O is actually bonded by 2 covalent bonds and 2 hydrogen bonds. So for example, for this case, it might be a bit hard to see, alright? So you can see that maybe for this molecule over here, alright, you have oxygen over here being bonded via 2 covalent bonds to 2 hydrogens, and then it's bonded by 2 hydrogen bonds to this hydrogen. Why? That's because water, it contains 2 lone pair and 2 hydrogen, right? So just nice, it can form 2 each. But then when they form this kind of structure, alright, sorry, to 4 hydrogen atoms. Right. So when it forms this kind of structure, around each water you will be something like a tetrahedral shape around each oxygen. So upon freezing, you can see that I introduce a lot of these kind of air pockets, empty spaces or empty voids, which doesn't contain anything. Right? Which means that its volume will be larger than that of water. So density, which is mass over volume, will be smaller. Alright? So remember this formula, rho is equal to m over v. For ice, there's a lot of empty space. In other words, volume increase. If volume increases, density will decrease, right? So that's why your ice has a lower density than water. Because water doesn't have all these regularly arrangements to incorporate the empty void. Alright? Now let's try this question. Once again, you are saying that covalent is a type of intermolecular force.
I'm sorry.
I'm asking for a predominant intermolecular force, right? So our first one, what's the predominant kind? Van der Waals. Can you form hydrogen bonds with itself? No, right?
No.
Remember, for intermolecular force, we are always referring to it forming interaction with itself. Unless the question asks you, which of these can form hydrogen bond with water, then you will be similar to a previous question they asked. So this is Van der Waals. Then this one, ethanol. Can you form hydrogen bond? Can, right? You have H connected to O. Even if you draw it out, don't draw, you should know that it can form hydrogen bond. Think about iodine. Just now already mentioned Van der Waals, right? Now, what do you find peculiar about their boiling point? For the first two, can you use Van der Waals to explain? You say that one of it has more electrons, therefore blah blah blah. Cannot, right? You can see that their size is about the same, 46. But this one has got higher boiling point. So why is that so? Hydrogen bond, right? We already mentioned hydrogen bond is generally stronger than Van der Waals. What about last case, iodine? If you compare these two, can you still say hydrogen bond is always strong?
No.
This case, you can see iodine, Van der Waals, but then is in fact much stronger than hydrogen bond. Why is it so?
Because
look at its MR. What can you tell me about MR compared to ethanol? It is much higher than MR, right?
Yeah.
In other words, the small amount of hydrogen bond now is more or less insignificant compared to the huge amount of van der Waals force. So you have to be flexible in your answer. Alright? So explain why the boiling points of dimethyl ether and ethanol deviate so greatly even though they share the same MR values. Alright, this is because ethanol contains hydrogen bonding between
So
its molecules. You cannot say itself. Itself, that means it interact with the same molecule between its molecules. While dimethyl ether, I just write dimethyl ether DME. While dimethyl ether contains van der Waals forces between its molecules. So then you say that hydrogen bond is stronger than van der Waals forces, right? Hence, more energy is required to overcome therefore ethanol has higher boiling point.
and keep calling them the wall now.
Explain why iodine has a higher boiling point. This one already explained. Alright. So you say that iodine has much more electrons than ethanol, such that the van der Waals forces, right, are significantly stronger than hydrogen bonds in water. Alright. And then you can go ahead and say more energy required, blah, 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 blah. Let's copy this. Therefore, iodine will have a higher boiling point. Okay, stop here. Next we will finish up the leftovers. Then we will do the questions, so you can go back and attempt the questions already.
So you only have 2 more lessons here before the end of the exam. I was wondering, like, do you have like
Practice papers.
You want to do practice papers?
questions or anything?
Anything just add on to the sheer number of practice papers we have already.
You also have, right? Practice papers, I guess.
For me,
Yeah,
as
but
in
my school only gave us 3.
3.
Yeah.
3 sets.
And
3 sets.
Go chang. I still got 2 research paper.
I have
I had no time.
6 practice papers in 7 practice
But
papers.
from what I know from my school is like they always like they will give us like different questions from the practice paper that they give us. So it's not very efficient.
The thing is, different school, their syllabus coverage is different for year 3.
Like for
You
physics.
try and find.
For physics,
If you don't have time to go through, then you can just